These are the high-voltage transmission lines stretching across the skies of the largest country on Earth. A massive energy network that is cold, dangerous, and almost never seen, yet silently powers the lives of millions of people every single day. Steel towers, dozens of meters tall, stand firmly across vast and unforgiving landscapes. Heavy conductors weighing tons are pulled tight across distances of hundreds, sometimes even thousands, of kilometers. And at the top of these towering structures, workers hang suspended high above the ground, operating in strong winds, freezing temperatures, and at heights where even a small mistake can quickly turn into a serious accident. Yet it is under conditions like these that one of the largest power transmission systems on the planet has been built, meter by meter. And in this video, join Mandarin Tech as we explore how Russia constructed high-voltage power lines across the largest country on Earth. Unlike many countries where electricity is generated close to population centers, Russia's power system is organized as a nationwide transmission network that connects major power plants, substations, and consumption areas through transmission corridors stretching continuously across vast territories. Because of this, the routes of high-voltage transmission lines cannot be chosen randomly. Before construction begins, the entire transmission corridor must be carefully surveyed to avoid densely populated areas, identify suitable river crossing locations, and ensure that construction equipment can reach the site through forests, open land, or regions covered by snow and ice for long periods of the year. Only after the transmission corridor has been precisely defined can the construction of the first transmission towers begin. When looking at a high-voltage transmission tower, the most visible part is always the steel structure rising dozens of meters into the air. But what actually keeps this massive structure standing firmly in place lies deep underground, within the load-bearing foundation beneath the tower base. Each tower foundation is constructed using reinforced concrete with high-strength anchor bolts embedded deep into the ground. This foundation carries the entire weight of the tower above and stabilizes the structure later when the conductors begin to be tensioned. In addition to supporting the tower's own structural load, the foundation must also resist large horizontal forces generated when conductors are stretched across spans that can reach hundreds of meters. Because of this, the placement accuracy of the anchor bolts and the quality of the foundation concrete are critical factors that determine the long-term stability of the entire transmission tower. Once the foundation reaches its required design strength, the erection of the steel tower structure can begin. In the most common method, steel components are transported to the site in multiple separate sections and assembled directly on location, level by level, from the bottom upward. The tower base is first secured to the anchor bolts, and then each additional section is lifted into position using cranes or specialized hoisting systems. As the height increases, workers must operate directly on the narrow steel members of the structure, moving with safety harnesses while coordinating continuously with ground crews to ensure every connection is tightened precisely into its intended position. However, in locations where terrain conditions allow better access, another construction method is often used to reduce working time at height. In this approach, the entire tower body can be fully assembled on the ground before being raised into a vertical position. Lifting equipment then rotates the structure gradually from a horizontal orientation to an upright position until the tower base aligns precisely with the prepared anchor bolts. This method significantly reduces assembly time at high elevations and improves overall construction safety. Whether the tower is erected section by section or lifted as a fully assembled structure from the ground, each transmission tower must undergo strict alignment and inspection before construction can proceed to the next stage. After the transmission tower structure has been fully erected and its structural stability has been verified, the next step begins directly on the tower's horizontal crossarms, installing the insulator strings. From a distance, they look like rows of small discs hanging in long chains beneath the steel arms of the tower. Each string is typically made up of multiple insulator discs connected together to create sufficient length to maintain the required electrical clearance distance. For high-voltage transmission lines, a single insulator string can reach several meters in length, depending on the system voltage level and the environmental conditions along the route. In areas with high humidity, strong winds, or heavy icing risk, the length of the insulator string is often increased to ensure long-term operational stability. The installation process is carried out directly at height as workers move along the tower body and across the crossarms to position each insulator string precisely at its designated suspension point. Individual insulator discs are connected using specialized metal fittings, and the completed strings are then attached to anchoring points on the crossarms through load-bearing suspension hardware. Throughout this process, every connection detail must be carefully inspected, since the full mechanical load of the conductors will later be transferred directly through this suspension system into the tower structure. Depending on the function of each tower along the transmission route, the configuration of the insulator strings may also vary. On suspension towers, the strings are typically installed vertically to keep the conductors aligned along their design path. At anchor towers or line angle locations, however, the insulator strings are installed at an inclined angle so they can withstand the large horizontal forces generated when the conductors are tensioned across the transmission line. In high-voltage transmission line construction, conductors cannot be pulled directly using simple pulling force from one side. Because of the heavy weight of the conductors and the span lengths between towers that can reach hundreds of meters, the pulling force must be precisely controlled from the very beginning to prevent sudden loads on the tower structures and to maintain conductor stability during movement. To achieve this, construction crews deploy a puller tensioner system on the ground, which acts as the central force control system for the entire stringing operation. At one end of the pulling section, the puller machine is securely anchored to the ground or to temporary anchoring points to generate a stable pulling force according to the design requirements. At the opposite end, the tensioner feeds the conductor from large reels at a continuously controlled speed while maintaining constant tension as the conductor moves across the spans between transmission towers. The coordination between these two machines keeps the conductor suspended above the terrain below, preventing contact with the ground, vegetation, or structures along the transmission corridor. Before the system begins operating, the large conductor reels are mounted onto the rotating stands of the tensioner and carefully aligned with the intended pulling direction along the route. At the same time, the entire pulling section must be continuously inspected to ensure that all suspension points on the towers are ready to receive the conductor as it moves forward. Throughout this process, the pulling force must not change suddenly, because even a small deviation can create large oscillations across the entire span length of the conductor. After the ground-based puller tensioner system and the stringing blocks installed on the crossarms of the transmission towers along the entire route have been fully set up, the first line introduced onto the route is not the main conductor, but the pilot line, a lightweight rope used to establish the initial pulling path for the entire stringing operation that follows. Under normal construction conditions, the pilot line is pulled from the ground using a puller machine and guided sequentially through each set of stringing blocks on the transmission towers. Because of its lightweight and easy controllability, the line can move smoothly across multiple spans without creating significant loads on the tower structures. Throughout this process, the pulling force is continuously coordinated with the tensioner system to keep the line at the correct elevation and prevent contact with the terrain or structures below the transmission corridor. This method is commonly used along routes that pass through flat terrain or areas where construction equipment can easily access the alignment. However, on modern transmission routes that cross complex terrain, such as mountainous forests, deep valleys, or long spans over major rivers, the pilot line is often installed using helicopters. In this method, the helicopter flies along the transmission route and places the pilot line through each set of stringing blocks at the tops of the towers. Because of the very light weight of the pilot line, the entire initial pulling path can be established quickly without the need to build access roads or move heavy equipment to each individual tower location. Whether the pilot line is pulled from the ground using a puller machine or deployed by helicopter from the air, it serves the same purpose: providing to create an accurate guiding path for stronger intermediate lines before the main electrical conductors are installed along the entire transmission route. If the pilot line only serves to establish the initial pulling path, then at this stage the construction site enters its most critical phase, installing the main conductors onto the transmission tower system. The process of pulling the main conductors begins at the tensioner station, where large conductor reels are mounted on specialized rotating stands to feed the cable at a controlled speed. At the pulling end of the section, the puller machine generates continuous pulling force to move the conductor along the transmission corridor that was previously established using the pilot line. Throughout this process, the conductor remains suspended in the air by the stringing blocks installed along the insulator strings, allowing it to pass across each span without contacting the ground or obstacles below. While the ground equipment is responsible for controlling the main pulling force, workers positioned on the towers directly monitor the movement of the conductor as it passes through each suspension point. They observe how the conductor moves through the pulleys, correct minor alignment deviations when necessary, and handle small vibrations or twisting that may occur as the conductor crosses long spans. The coordination between the ground-based equipment and the crews working at height ensures that the conductor moves smoothly and follows the intended alignment throughout the entire pulling process. Once the conductors have been fully positioned along the transmission route, the next step is to adjust their working sag. This is a critical technical operation that ensures the conductors reach their correct operating height according to the design requirements, while maintaining safe clearance distances from the ground, structures below, and adjacent phases under all temperature conditions and environmental loading scenarios. After the main conductors have been pulled into position and their sag has been adjusted according to the design specifications, the construction site begins transitioning the conductors from their temporary suspended condition on the stringing blocks into their final operating configuration. This stage includes 2 consecutive operations: installing armor rods at the suspension points and performing clipping in to secure the conductors into their permanent hardware attachments. First, the crews install the armor rods, preformed steel rods shaped to match the diameter of the conductor and wrapped directly around the conductor at the suspension clamp locations. Armor rods act as a mechanical cushioning layer between the conductor and the clamp, helping distribute contact stress and reduce conductor wear during long-term operation. In practice, armor rods can be installed using 2 different approaches depending on site conditions. On many projects, especially after the conductor has already been fully tensioned along the route, workers install the armor rods directly at height on each tower. This method allows precise positioning based on the actual suspension clamp configuration and is particularly suitable for routes that pass through complex terrain or include long spans, where preparing the components in advance from the ground would be difficult to perform accurately. On routes with easier access conditions, however, armor rods can be installed on the ground before the conductor is lifted onto the tower system. This approach reduces the amount of work required at height, shortens installation time at the suspension points, and helps accelerate overall construction progress along long transmission sections. Once the armor rods have been properly positioned, the conductor is secured into its permanent suspension hardware in a step known as clipping in. At suspension towers, the conductor is fixed using suspension clamps, which allow small movements caused by wind and temperature changes during operation. At anchor towers or line angle locations, the conductor is secured using strain clamps designed to withstand the longitudinal tension along the transmission line. From this point forward, the conductor is considered to be in its final operational configuration within the transmission system. From steel foundations buried deep underground, to transmission towers rising dozens of meters high across harsh terrain, and to heavy conductors weighing tons being precisely pulled across each span, the construction of a high-voltage transmission line is actually a complex engineering operation that takes place simultaneously on the ground and high above in the air. Every insulator string, every stringing pulley system, every set of armor rods, and even each small suspension clamp installed at the top of the towers plays an essential role in ensuring electricity can travel safely across hundreds of kilometers. something most of us rarely notice when we look up at the sky each day. This is how these silent, electric highways connect power plants to cities, industrial zones, and millions of homes around the world. If you want to continue discovering how massive infrastructure systems like this are built in the real world, don't forget to like, subscribe, and follow Mandarin Tech as we take you inside the engineering projects that keep the modern world running every day.